Let's do some exercise questions. The first question is, calculate the number of states per cubic meter of sodium in 3s band. The density of sodium is 1013 kg per meter cube. How many of them are empty? So the first question. So density is given. It is 1013 kilogram per meter cube. Now let's consider volume to be 1 meter cube. So what will be the mass? Mass will be density into volume, because density is mass over volume. So in 1 meter cube 1013 kg will be there. So number of atoms will be Avogadro number into number of moles. Now Avogadro number and number of moles can be found out by given mass over molar mass. So the molar mass for sodium is 23 gram, and also we need to take this mass in gram. So 1013 into 10 to the power 3 gram. So number of atoms will be equal to Avogadro number 6.022 into 10 to the power 23 into given mass is 1013 into 10 to the power 3 gram over molar mass, that is 23 gram. So after solving this, you will get approximately 264.26 into 10 to the power 26. So this many atoms are there. So A part, total number of states. Total number of states are 2n. So it is always twice of the number of atoms. So 2 into 264.26 into 10 to the power 26. So it will be 5.3 into 10 to the power 28. Then total number of unoccupied states. So half of the total states are unoccupied, that is 2.65 into 10 to the power 28. This is 2.65 into 10 to the power 28. So half of the total states are unoccupied. In question 2, we have a pure semiconductor. The number of conduction electrons is given. How many holes are there in a sample size of 1 centimeter into 1 centimeter into 1 millimeter? So question number 2. So in a pure semiconductor, that is an intrinsic semiconductor, number of conduction electrons is equal to number of holes. In intrinsic semiconductor, holes and electrons are equal in number. Now volume that is given to us is 1 centimeter into 1 centimeter into 1 millimeter. Let's convert it into meter. So it will be 10 to the power minus 2 meter into 10 to the power minus 2 meter into 10 to the power minus 3 meters. So volume will be 10 to the power minus 7 meter cube. So number of electrons will be 6 into 10 to the power 19 into 10 to the power minus 7. These are the number of electrons per cubic meter. Okay, that's why we are multiplying it with meter cube. So it will give us 6 into 10 to the power 12 electrons. So this will also be the number of holes, because in intrinsic or pure semiconductor, holes and electrons number are same. In question 3, indium antimonide has a band gap of 0.23 eV between valence and conduction band. We need to find the temperature at which kT equals the band gap. So this is the third question. Energy that is given is 0.23 eV. We know that K's value is 1.38 into 10 to the power minus 23. So energy must be equal to kT. So temperature must be equal to energy over K. So 0.23, it is in EV, so converting it into joule, 1.6 into 10 to the power minus 19 over K, 1.38 into 10 to the power minus 23. So temperature will be 0.2676 into 10 to the power 4 or 2670 Kelvin. So this much temperature must be there. In question 4, the band gap for silicon is 1.1 eV. We need to find the ratio of band gap to kT for silicon at room temperature 300 Kelvin. And at what temperature does this ratio become 1/10 of the value which is at 300 Kelvin. So this is the fourth question. So band gap is given 1.1 eV. Temperature is 300 Kelvin. At room temperature, this is the band gap. At room temperature, this one is the band gap. Now first we need to find the ratio. So band gap over kT, 1.1 over 1.38 into 10 to the power minus 23 into 300, that is 3 into 10 to the power 2 Kelvin. So we will get 42.53 or approximately 43. Now if the ratio is 4.253, so 1/10, okay, 1/10 of 42.53 is 4.253. So we need to find the temperature. So the temperature will be so after solving this, there is a slight mistake here. We also need to convert that part into joule. So it was 1.6 into 10 to the power minus 19 also. So 4 will remain, and here also This was in EV, so we need to convert it into joule. Okay, so now after solving this, we will get 3000.47 Kelvin. So at this temperature, the ratio will be 1/10 of the ratio at the temperature 300 Kelvin. In question 5, when a semiconducting material is doped with an impurity, new acceptor levels are created. In a particular thermal collision, a valence electron receives an energy equal to 2 kT and just reaches one of the acceptor levels. Assuming that the energy of electron was at the top edge of the valence band and that the temperature T is equal to 300 Kelvin, find the energy of the acceptor level above the valence band. So this is the fifth question. So what is the energy gap between valence band and acceptor band? So it is twice of kT. So that is 2 into 1.38 into 10 to the power minus 23 into 300. So the energy gap will be 2 into 1.38 into 3 into 10 to the power minus 21 joule. Converting it into EV, we can divide it by 1.6 into 10 to the power minus 19. So it will be 5.175 into 10 to the power minus 2 EV, or 51.75 into 10 to the power minus 3 EV, or 51.75 milli electron volt, approximately around 50 milli electron volt. In question 6, the band gap between valence band and conduction band in ZNO is 3.2 eV. Suppose an electron in conduction band combines with hole in the valence band and excess energy is released in the form of EM radiation. We need to find the maximum wavelength that can be emitted in this process. So the sixth question. So energy gap is given 3.2 eV. It is quite simple now. We know that energy is h over lambda, h nu, which is h over lambda. So 3.2 equal to h is 6.63 into 10 to the power minus 34 into speed of light, which is 3 into 10 to the power 8 over lambda. So lambda will come out to be around 388.1 nanometer, that is into 10 to the power minus 9 meters. So this will be the value. In question 7, suppose the energy liberated in recombination of whole electron pair is converted into EM wave or EM radiation. If maximum wavelength emitted is 820 nanometer, what is the band gap? So like the previous question, E equal to hc over lambda, E equal to 1242 eV into nanometer, the value of hc in eV nanometer, over wavelength is given to us, it is 820 nanometer. So we will have the value to be around 1.5 eV. By the way, this part is in eV, so you can convert it into joule by multiplying it with 1.6 into 10 to the power minus 19. So 1.5 eV will be the energy. In question 8, find the maximum wavelength of EM radiation which can create a whole electron pair in germanium. Band gap is 0.65 eV. Eighth one. So band gap is 0.65 eV and we need to find the wavelength. So E equal to Hc over lambda. So 0.65 eV equal to 1242 eV into nanometer over wavelength. So wavelength will be 1242 over 0.65 eV into nanometer. So wavelength will come out to be 1910.7 into 10 to the power minus 9 meter, or approximately 1.9 into 10 to the power minus 5 meters. So this much wavelength if energy gap is this much. In question 9, in a photodiode the conductivity increases when material is exposed to light. It is found that conductivity changes only if wavelength is less than 620 nanometer. What is the band gap? So the ninth question. So again same thing, band gap will be the energy required to overcome the gap. So it is Hc over lambda 1242 eV nanometer over wavelength which is given 620 nanometer. So energy that will be required to overcome the gap will be, after solving this, 2 eV. So this much energy is required to overcome the gap. In question 10, del E denotes the energy gap between valence band and conduction band. Population of conduction electrons and of holes is roughly proportional to e to the power minus del E over 2 kT. We need to find the ratio of concentration of conduction electrons in diamond to that in silicon at 300 Kelvin. Del E is given. How many conduction electrons are likely to be in 1 cubic meter of diamond? So this is the 10th one. So first of all, it is given that N is number of electrons is equal to this much. Now del E for diamond is 6 eV and del E for silicon is 1.1 eV. So for diamond, let's put the value at the place of del E, 6 eV over 2 kT. So 2 into 300 into 8.2 into 8.6 into 10 to the power minus 5 into 300. This value is in converted for EV, okay? Because of that, K's value is this here, 8.6 into 10 to the power minus 5. And similarly, N of silicon will be e to the power minus 1.1 over 2 into 8.62 into 10 to the power minus 5 into 300. So when we take the ratio Nd over N silicon, we will have 4.1 14772 into 10 to the power minus 51 over 5.7978 into 10 to the power minus 10, 7.15 into 10 to the power minus 42. So this is the ratio. And the second part was as we have more energy gap, so big energy gap is quite high. So in diamond, because of the high energy gap, conduction band electrons per cubic meter will be approximately 0. That is because the energy gap is so high, almost no electron will be able to go from valence band to conduction band. In question 11, conductivity of a pure semiconductor is roughly given. Now band gap also given. By what factor does the conductivity of pure germanium increase as the temperature is raised from 4 Kelvin to 300 Kelvin? So this is the 11th one. So conductivity is given by this formula. This is at 4 degree. This is at 4 Kelvin. Now conductivity let's try to put the value of temperature and find the value at 4 Kelvin. E minus 0.74 over 2 into 8.62 into 10 to the power minus 5 into 4. So it will be 8 into e to the power minus 1073.08, and at 300 Kelvin sigma will be 300 3 by 2 e to the power minus 0.67 over 2 into 8.62 into 10 to the power minus 5 into 3 into 10 to the power 2, 300. Okay, so from here sigma comes out to be 3 into 1730 over 8 e to the power minus 12.95. So let's take the ratio at 4 degree, at 300 degree. Eight into e to the power minus 1073.08 over 3 into 1730 over 8. So we can multiply with 8 above, so it will become 8 into 8, 64, and into e to the power 12.95 minus 12.95. So this ratio will be approximately 64 over 3 into 1730 e to the power minus 1060.13, because this will go upstairs and will be added like this. So this will be the approximate ratio.